She hates me. Probably. Alright. So anyway, today, Laplace transforms.
Do we have to write it like that?
No, but they do use the script L a lot for it. Okay, can you start working, please? Shh. Thank you. Anyway, so what we're going to be doing is this. We're going to be transforming our functions. We'll have, say, functions of t. We're going to transform them to become functions of s. And you're like, what's the point? Well, now. It's not just because we want to. We're going to turn a giant calculus problem into a giant algebra problem.
I like it.
Is that better or worse? Well, it depends. There's some where you can't make it better. Sometimes it makes it a lot better. Other times it's like, oh my gosh. Now,
So what do you mean by algebra? Do you mean like a two-step equation?
straight up algebra problem. You hit solve, the computer goes, oh, boom, there it is. X of s equals this. And then you're going to then, of course, transform it back to f of t. So, again, here's the deal. So we have some f prime of t, right? Equation, I should say, right? We're going to transform that to some f prime of s equation of some sort. You with me? And then we're going to turn back around. We're going to solve for, you know, some function of s is equal to blah, blah, blah. And then we're going to untransform it to get back to, I'll just write it as some f of t, some other form of t.
Back to f of t or f prime?
It'll always, no. We're always trying to get from dy dt or whatever, get back to y of t, yes? So we're going to get back to the actual solution. We just take this circuitous route, which is actually a lot faster and easier a lot of times. So the question is how do we do it? So, well, Levi, in stats, you recall we talked about the expected value, right, of x, and on a normal distribution, that is the integral from negative infinity to infinity of x times, and then what, you know, I'll just write the normal distribution here, the normal PDF. So if you integrate this thing over the entire course from negative infinity to infinity, you get the expected value, which in that case happens to be x bar. So it's something that we do all the time. But the Laplace transform is similar but a little different. So the Laplace transform of, what should we say, the Laplace, can you shut up? You're freaking me out, man. Is equal to the integral of e to the negative st times our f of t dt, and we're going to integrate from 0 to infinity because it doesn't go from negative infinity, it only goes from 0 to infinity. And this is what we'd like to think of this as the expected value of e to the negative st. It's something that we do all the time in stats, other places, and real stats. And we just say, so instead of being the expected value of x times this times this f of x, it's just e to the negative st times this guy. Now, we're integrating with respect to t. That means everything except the s's are going to cancel out, yes? Right? So you're going to, when you're all done, you're going to have some formula of s, some f of s, when it's all said and done. Now you're like, there's functions that we use all the time, like e to the at. We're going to have to memorize those ones. And we're going to. Cosines and sines, yeah. You know, things that are repeated root things. Some of these other ones we use all the time. They should stick in your head. Others of them won't stick in your head, but we can work them out. Okay? So what we're going to do today is we're going to find a few of these Laplace transforms. We're not going to do them all today. And then we're going to say, well, wait a minute. Can you transform a derivative? Yes. Which is the whole point. But if you can transform the derivative and the second derivative into also functions of s, then when you're all done, you can solve these problems just like a freaking algebra problem. Muy bueno. Muy easy. Here we go. So the game becomes this. So for instance, if I have my function of t is, let's do a nice easy one, e to the at. Doesn't matter what a is right now. Well, do it in general. Then the Laplace transform of that, I'm going to transform it, is going to be equal to the integral from 0 to infinity of e to the negative st times e to the at dt. Nice. But I notice that there's multiplication. And when the bases are the same, I should probably add the exponents, eh? Probs. So we could probs do this. And I could probably write it a number of ways, but I can just write it like this for right now. But then I'm like, well, they have a t in common, right? And so this is kind of a big deal, and there's a reason for why this has to be. This is an improper integral, yes? It's going to infinity? If I pulled out a t and left it as a minus s, what happens to this thing as t goes to infinity? It blows up. This one would be muy easy. I can do that, no problem. So what I'm going to do is pull a negative t out of both of those fellers. Because that guy actually converges. That's a big deal, Jacob Hawkins. If it does not converge, we are screwed. Correct. Thank you, Joe. I like it. Now, what is the antiderivative? Well, of course, it is negative 1 over s minus a e to the negative t s minus a from 0 to infinity, but not beyond. So do tell, what is the limit as t goes to infinity of negative 1 over s minus a e to the minus t s minus a minus, and then if you put 0 in, this piece just becomes 1, so you're going to get minus 1 over s minus a. Yeah, so again, I put 0 in on the bottom end, I get this, but I can't put infinity in, so I take the limit. So what's happening to e to the negative t as t goes to infinity?
Switching 0.
This bit going to 0. It better go to 0 every time when we play one of these games, or we are screwed. Wait a minute, Mr. Grimm, are you saying that the Laplace transform of e to the at is equal to 1 over s minus a? That's exactly what I'm saying. So in the future, whenever you see e to the 3t, you're going to write 1 over s minus 3. If you see e to the negative t, you're going to write e to the s, or 1 over s plus 1. If you have 5 e to the negative t, you're going to have 5 over s plus 1. And it's that easy. Because I never have to do this again. In the future, for instance, if I said to you, hey, what is the Laplace transform of 5 e to the negative 2t, you are literally going to write 5 over s plus 2. This is a 5. I try to stay away. It made it worse. I try to stay away from 5s when we're doing this. Don't ask me why they used s. I don't know. Personally, on the calculator, when we're doing this later on, we're going to use z instead because it's on its own key and it's easy to use. Plus, it's harder to screw it up. Yeah, that's it. Now, another function that we use all the time is cosine. So if I want to do the Laplace transform of cosine of kt, like so. What would I do here? I feel like I would, I'd probably do this. The integral from 0 to infinity of e to the negative st cosine kt dt. Oh, that's awesome. How do you integrate that, man? Remember?
Go around the merry-go-round.
Integration by parts. Twice. Right? So let's make it happen. Let's make it happen, dog. So, obviously, who's which? Oops. Remember, Liotte, technically speaking, I probably should have done this. Doesn't really make any difference because they're the same. So it's negative k sine kt. And then, of course, dv is e to the minus st. And, of course, v is equal to 1 over s negative e to the minus st. So it's going to be negative 1 over s e to the minus st cosine of kt minus the integral of, now it's v du, yes? So notice how they're both negative already, yes? So it's still going to be negative. going to pull that 1 over. I'm going to pull that k over s out front, though. Okay? And that's going to leave me with e to the minus st sine kt. Like so.
Wait, so
Wait, so what?
it's VU,
It's uv
UV,
minus the integral of v du.
right? Okay.
Right. We're going to play it again, right?
I don't write that backwards.
So u is equal to sine kt. du is equal to k cosine kt. Of course, dv so remember it's minus k over s times, and then everything inside is going to be minus 1 over s e to the minus st sine kt minus, it's minus the integral, but it's already negative here, so I'm going to pull that out front, k over s, and then it's e to the minus st cosine kt. What are you doing? Do you need some? Do you need something? A book?
I feel bloated.
Well, good. That's lovely. That's great. Just be quiet about it.
I wasn't talking.
Shh. Well, maybe you're bothering the other guy because he was bothering me.
I'm missing something.
Don't waste my time. That's kind of annoying. Okay? Now, let's go ahead and multiply this k over s business through, yes?
Give me just a second.
And while we're doing that, I'm going to rewrite the other side where it was, okay? Bwomp. It is a little disgusting. It's not too bad, though. So it's going to be plus k over s squared, right? And it's positive e to the minus st sine kt. And it's going to be minus k squared over s squared. That's hot. E to the minus st cosine kt dt. Oh, there's a doohoo there somewhere. No. So we move that over yonder. So we're going to have, that's s over there, right? That's s squared over s squared right here. True? Because it's 1.
Yeah.
What are you moving on?
Well,
Oh, yes.
so
Okay.
I'm gonna
You
move
have
it.
to make it so you can move it over.
So it's going to be s squared plus k squared over s squared. Run down in a minute, yes?
Yep.
S squared plus k squared over s squared. Integral. I'm just going to say integral. Okay? I'm just going to say integral. Okay? Because I don't feel like doing it anymore. I don't really care. 1 over s e to the minus st cosine kt plus k over s squared e to the minus st sine kt. So then I'm going to multiply by s squared over s squared plus k squared, yes?
Okay, I'm still not following how you.
Not following where? Where?
I'm not following the s squared over s squared.
Problem. It's k squared over s squared, yes?
Yeah.
I'm going to add that over. I need a common denominator. Currently it's 1. So I just make it s squared over s squared. And then I have the same denominator. So when I plus this fella over there, I'm going to have s squared plus k squared on top over s squared. They have a common denominator.
He factors out the integral part from the left side when you move it over.
Okay, now. Okay, now I need to evaluate this guy. This is the integral. This is the integral. I need to go from 0 to infinity, yes? Okay. Now, we are going to wave our hands at it slowly but easily here. So what happens when you put infinity in here? Well, this piece here is going to 0, yes? Now that we know that because whose theorem here? Who? What's his name? Lopito, yes? Because this is really e to the st on the bottom, yes?
Yeah.
So who? Well, this is doing whatever it's doing. It's just bouncing back and forth. But the bottom is getting huge, so that means the whole thing is going to 0, yes? And what about this piece here? It's also going to 0. So at the top end, we've got 0 minus. Now what's happening on the bottom end is you're going to 0. As you go into 0, this is 1. This is also 1. So I'm getting negative 1 over s. And what's happening to this piece here? 1 and 0. So this piece is going away. Times s squared over s squared plus k squared. Why are people bothering me? Can you fix my computer? I can't watch ESPN anymore. Literally, that's what it is. Anyway, so what happens if I multiply this out? It's going to be positive, obviously, yes? S over s squared plus k squared. This is the Laplace transform of cosine of kt. Okay, we'll get the sign in a minute, yep. It would be nice if they were the same. Oh, but they're not.
Negative s over s squared.
Is that working for you there? Ah. Well, let's try sine. Let's set up sine and see what you think. So obviously I want to do this. Sine kt. Try that. See what you think. It ain't that bad. Try it. Go ahead. Yeah, try it yourself. I can tell you what the answer is when it's done. I know what the answer is. Right? You know, I have to go through all the work myself. Way too much trouble.
Better go fix some of the ESPN first.
We take attendance.
I have a note from Mr. Ford that why I was late. I was doing a test. Oh, really?
Oh, I see.
Our v is negative 1 over s. Using negative s. Yeah. Here, I'll put it back up so you can look at it. It's basically you're just.
know the answer part of this.
Well, no, for sure. I mean, you know what some of it's going to look like. It's going to look like this mess. I mean, it's going to look very similar.
Yeah, but when you get to
Say, when you're, look, Corey's following along, kind of what we're doing here. It's going to be the same basic premise, right? There's going to be a negative in a different place or two, because you're doing derivative cosine to derivative sine and stuff. But it's going to be similar. The idea is once you hang these, the same ones are going to show up again and again and again, so you'll get the cars to memorize them. Sines, cosines, e to the x's and stuff will show up all the time. Of course, there's some other ones that will show up all the time too. Some of which you'll remember, some will be like, oh crap, I forgot that one. So you're like, hey, what happens if it's a really gross one on the test? Well, the early ones on the test you're going to do by hand. You need to memorize them, and I'll have some tables that you can look at. But then there are some really ugly, disgusting, oh my gosh, gross ones. Then we'll use the computers to actually let it go through and do some of this math. It'll be fun. I don't know fun.
yeah, stuff.
Not gonna lie to you, it's not always fun.
Oh, that's why.
Almost there.
Doing phone is one thing until you get to one step.
What step?
I still don't. I just not following you.
Okay, bro.
Bruh.
I get
Bro,
the one.
what if this was 1/5, yo? What if this was 1/5? What if this was 1/5?
Like if you just put a number in.
What if that? It literally, that was 1 over 5.
Okay.
Then this is 1. Wouldn't you make this 5 over 5?
Yeah.
And then it would be 5/5 plus 1/5 would be 6/5.
Mm-hmm.
That's all it's doing.
6/5. 3/5.
And then it'd be 6/5, and I would like divide by 6/5 and multiply by 6.
And that's why that goes away.
Yeah, that's what I'm talking about. Yeah. So good. Yeah, yeah. I'm gonna go freeze and try to do them around.
We got it.
Let's race. Give you a head start, huh? for gosh sakes. All right, negative 1 over s. T sine t plus 1 over s. K over s. Cosine. Nope.
Because that's just one.
Now I'm following. So this right here, is that going to go like that?
Okay, we good?
No, not yet.
Yes. Well, actually, I got all the way to the last step, but I'm pretty sure I know what the answer is.
So then multiply by the reciprocal. Yeah.
What do you get?
I know that it has this flipped in it. I was doing
Sort of, but not really.
I was
that's
doing
part of it.
Yeah, that's not the final answer, but I was doing that really quick.
You good?
Where would I go from here?
I feel like I'm getting the exact
Put a big fat bracket on that whole thing, and multiply by that reciprocal out front. So that's squared over. All right, so here you go. I will get you to here. Let's see what you think. We're good to hear, yes? I haven't put it to the other side yet?
Yeah.
Okay, so obviously you need to have s squared over here again, yes? So I'm going to have s squared plus k squared. Well, okay, so I'm going to have s squared plus k squared over s squared, right? Then I'm going to multiply it back over. So it's going to be s squared over s squared plus k squared. Brackets, and then this mess.
That's right.
What do you mean? Is that where your problem is right there?
No, that's just the step I was at.
Oh, okay. So we're all right about here then, yes? And again, we're going to evaluate it from 0 to infinity, yes? So by the same relation, from the same thought process as last time, this thing is going to 0 at infinity. So what is this fella? So it's going to be 0 on the top end. Okay, minus. And then at the bottom end, you throw 0 in. This piece goes to 0 because it's sine. This is 1, this is 1. So we're going to have minus k over s squared. Right? And all of that is inside of there. Now we're going to multiply by this. And so our answer is going to become, this is positive, and then the s squareds are going to cancel, and you're going to be left with k over s squared plus k squared. That guy is the Laplace transform of sine of kt. So Corey, if you wanted to do the Laplace transform of, I don't know, 3 sine 7t, or whatever, okay, what would you have? It'd be 3, obviously, over, or 3 times, let's just do this part one at a time. So k is 7. So 7 over S squared plus 49.
Right.
So, that's it. You're literally following the rules, the steps. Furthermore, wait, what would happen if, oh my gosh, check this out. What if you had 11 over S?
What's the S?
We haven't used that yet.
Oh my god, dude, that's what I literally just said. That's what I said earlier. Stop. That's the whole beautiful thing about it. We are changing from functions of t to functions of s for no apparent reason at first, other than to be able to allow us to use, all right, the algebra that we're going to use later on. So for today, it's literally just changing out variables. Okay? But later on, some pretty cool stuff's going to show up. Our good friend, the characteristic equation, is going to show its face again.
Oh man.
Every time.
Again?
Not r squared plus 4r plus 4 anymore. No, it's going to be s squared plus 4. And, oh wait, that's like a repeated root one. It is. And so we're going to have to figure out what happens if you have a repeated root and stuff like this. All these things are going to show up as we're doing this. So just stay with me, bear with me. Now, Corey, if I saw this fellow here, sure. What is going on with this guy? If I wanted to do the inverse Laplace of this fellow, the very first thing I would say to myself is, wait, this 11, yo, I can bring that out front because it's linear like that.
It was 21.
It was 11 on top, yo. No, it's a different problem, yo. I just said, suppose this was a different random problem I just made up.
Oh, okay, because the other one was 21.
No, yeah.
Or 49.
Yeah, whatever. So wait a minute. It's something over s squared plus 3. Well, you know what? It's not an s on top. So it's not cosine. It must be sine of some sort. And you're like, oh, yeah, that's great. It must be the sine of the square root of 3t. Not so fast. If that were true, there would have to be a square root of 3 on top, yes? Because this is k squared. There has to be a k on top. So watch me fix it. Are you watching? Are you ready? Are you watching? Put a square root of 3 on top. Put a square root of 3 on the bottom. Ah! Done. So later on, we're going to get down to answers that look like this. You're like, okay, great. Now where did it come from? Well, it came from this fellow. Okay. Or someone else. It's not very hard. Like for instance, you're like, oh, okay, I got this answer. I got this. Ah, stop it. What is this? Well,
That one's supposed to be S squared on the first one too, right?
no.
Oh.
Interesting to know. You're like, Mr. Grimm, this is like limits. That is, I could do each piece individually when it's a sum. That's exactly right. Not when it's a product, though. That's different. We'll have to use a thing called convolution.
Not like that.
But when it's addition, I can do them individually. So what does the first one look like? What's that? 3 e to the negative 16. That is 100% correct. And the second one is, I see an s on top, so it's cosine. So it's plus 7 cosine. Oh, for God's sakes. Cosine of 2t. Do not screw that up. Not 4t, 2t. So we'll use these quite a bit. Get comfortable with them. You're going to like them. Or not do well. All right, so, yeah. Wait a minute. What if, hypothetically, you have this fella? Oh, it's a product. But wait, t e to the at, we use this guy a lot because we have repeated root ones, yes? So this one's probably going to be a big deal. Probably a big deal, yeah.
Do we have time later? Can we do one of those where it equals 0?
Well, we'll see.
Okay.
Well, we'll probably have time to do it because we're going to do a nice, we'll talk about we'll probably define today in a few minutes, we'll define how to do the Laplace transform of a derivative. Because once we do that, then the rest of it's not too bad. But I just really kind of want to get to how we get these today.
Okay.
Okay, so this one here. Yeah. So Obviously, it's the integral of 0 to infinity of e to the minus st times e to the at times t, dt. Which is, let's be honest, that is just 0. Let's play the same game we did before. I'm going to write t in front. I'm going to write e to the negative t s minus a. Right? But once you get to here, you recognize this format, yes? How do you integrate t e to the negative t? Integration by parts again. Integration by parts. And since we're going to have to do it a couple of times, but it is going to go away, that tabular method would be handy, yes, wouldn't it? So we go t, 1, 0, right? Take derivative of t, derivative of, which is 1, take derivative of that, 0, right? You don't have to include that if you don't want to, the 0 part. And then the other one is, well, it's e to the negative t s minus a. The antiderivative of that is negative 1 over s minus a, e to the minus t over s minus a, like that. And the derivative of that is going to be positive 1 over s minus a squared. I think. No, I don't think I know. That's great. Boom. And if you recall that tabular method, it was this times this minus that times that. Right? So it's going to be negative t over s minus a e to the minus t s minus a minus 1 over s minus a squared e to the minus t s minus a. And again, we're going to evaluate that from 0 to infinity. Check it out. It's going to be infinity times 0. That sucks. But we know how to do this well. This feller would like to be on the bottom, yes?
It would be.
T over e to the t. Who wins? Obviously, e to the t wins. The thing's going to 0. This one's also going to 0. So 0 at the top end, which it pretty always better be that. Now, on the bottom end, you stick a 0 into here, you're going to get 0 times 1, which is just straight up 0. That's nice. Put an e to the 0 in here. This is 1. So it's going to be 0 minus. And it's going to be 1 over s minus a squared. So my answer is simply 1 over s minus a squared. This is the Laplace transform of t e to the a t. And we can just do these until we're blue in the face. Now, Jacob, I've had about enough of this foolishness. What if we run across one? This is a good review of Calc 2, by the way, yes? It's fun. I've enjoyed this time we've had today. I'm done now. I don't care anymore. So, what if I wanted to do the Laplace transform of just t? I'll tell you what I'm going to do. I'm going to break out my freaking calculator. That's what I'm going to do. I'm going to do the integral on my calculator. God, I hate you. Now I'm just going to integrate this thing. I'm just going to go t times e to the negative z times t with respect to t. Boom. I am not going to try to go from 0 to infinity because Betsy will not like that. I just want to know what is the antiderivative. Right? So you should be playing along with your calculator. It would be nice. If you have one, you should drag it out. If you don't have one, you should get one. Use it and play along. What do you get?
E to the negative zt times t squared over 2.
Right? It's beautiful. So, hang on. What was it? T times?
E to the negative ct.
Oops. Nope. That's what I thought. I thought it was a little something different, dude. What you got? If you didn't got it, you should got that. It just looks funny to read.
Maybe I need to type it.
You must type the times in.
Yeah, I didn't type that.
You must type it in. Anyway, that's what it should be. So, read that to me again. What is it?
Parentheses,
God, I hate you. Go ahead.
negative t over z,
I'll show you who's boss, you piece of crap.
It doesn't really matter what.
No, I just used Z in the thing. I should have gone back to putting it back to the S's,
Well,
okay?
it doesn't confuse
But it
me.
doesn't really confuse most of us. It's just, you have to go hit alpha to get S, and that's a pain in the butt. There we go.
Like X.
Yeah, I just don't like to use X because X is what we kind of, I mean, well, I just don't like to use X. I like to use mine. Okay, you're going to do it now. Okay, good. So parentheses, what is it?
negative t over z, minus 1 over z squared, all that times e to the negative z, tz, negative tz.
Okay, cool. So at the top end, again, this is just this times this, yes? When you plug infinity in here, you're going to get negative t over e to the zt, right? That's who wins going to infinity. The bottom does, so it goes to 0. Same thing's going to happen here because this is on the bottom. Of course, it's going to 0. So it's going to be 0 on the top end minus. Now, if you plug in 0, of course, this first piece is 0, yes? 0 over something, right? And then minus, and then the other end is what? So they plug 0 into here. This, of course, is just 1, so that's cute. And then it's just going to be 1 over z squared, negative. Or it's just, yeah, I'm sorry, that's what it is right there. And so our answer simply is 1 over, well, 1 over s squared. This is the Laplace transform of t. That's cool. What if it was t squared? I wonder if there's a pattern. What now? What'd you say? Is it cubed? I don't know. Let's find out. So a fella could come in here and just go squared. There's this mess. That's great. Whatever. Clearly at the top end, you put infinity into this thing, and of course the whole top end is 0. Yes? I think we're all pretty fairly clear with that. If you throw in 0, it's going to be 0 squared, so 0. You're going to have 0 is, well, 0. And then you're not going to have 0. Not going to have 0. So it's going to be negative, it's going to be 0 minus, and then it's going to be a negative 2 over z cubed. So it's going to be 2 over z cubed, or 2 over s cubed. So you weren't wrong about the cubing. I wonder,
Could you go back to the calculator?
oops, what would happen if we did a cubic? What do you need?
Could I calculate? That's good.
Now, if you do cube, of course, it's what? Nope, that's a 6, dummy. There you go. There's this mess. Clearly at the top end, when t is infinity, we got a problem. We got zeros, zeros, zeros all the way down. Of course, until you get to the bottom one. The whole top end is 0, I should say. So the whole top end is 0 minus. And then you come back in, and you put zeros in. Okay, and everything else is going to be 0 except for the bottom, which of course is going to be 6 over s cubed, or s to the 4th rather. And it's going to be negative 6 over s to the 4th. So my answer is 6 over s to the 4th. Huh. Wonder if there's a pattern there.
Was the 2 supposed to be negative on that one?
No, because it was minus and minus.
Okay.
What? The next one's 24? Oh my gosh. The next one, for t to the 4th,
It's like a factorial.
it is like a factorial over s to the 5th. So what's the pattern? If you have the Laplace transform of t to the n, what does it come out to be? It is
N factorial.
n factorial over
T to the n plus 1.
t to the n plus 1. Bam! Well, I'm sorry, s to the n plus 1. Thank you. That's it. Back in the day, you know how long it took to discover those by hand? Wow. Calculator, boom, boom, boom. Oh, geez, there's a pattern. How about that? What do you think? What?
Such that, yeah, I was just typing in such that t equals 0.
Yeah, that'll work too. Nice. That's good.
It was like,
All right, so that's cool. Now, screw 'em. But wait a minute. I feel like I should. What if I had a derivative? What if I had the Laplace transform of x prime of t.
Oh, man. This is how we're going to derive some of
It turns out that it's like this. It is s times x of s minus x of 0.
We can use that to solve the
Just-
equations.
Yeah, when we get there, yeah. That's the whole point. And so on, and so on, and so forth. What's that? Sure, can we do third ones? Yes, we could.
Wait.
What?
Okay, yeah. That's a good question. I don't think I need to roll. Yeah, are you just seeing me just rip in?
They're asking.
Wait a second.
Now, today that's all we're going to talk about. Okay, we could do third derivatives, fourth derivatives, fifth derivatives, a pattern for those two. We pretty much stick with second orders, first and second orders. So pretty much everything we're going to do, we can deal with from right here. This is a big deal. These two things right here are huge. You must commit them to memory. Don't not do that. Now, wait a minute. Dude, check this out. Check this out. But dude, check it out. It's just a filler variable for now. That's all it is. And it's all it's ever going to be for us in this class period. If you were in a linear algebra class, you could talk about, well, how did it map over there? What do we do? And that's great. We don't worry about that. We just use it. Okay? It is so similar to things that you do. Well, like for instance, I taught you guys, well, somebody did, how to solve equations using matrices, yes? And you could do them without even understanding how they work, with the inverse and all this crap. Or use the regression calculator thing on your calculator. Well, it spit out A and a B. Yeah, do you know where it came from? No. Do you care? No. Just going to use it. Similar idea. Okay, now watch this. This is exciting. So x double prime plus 5x prime plus 6x. Wait for it. Look how gross this one's going to be. No, I want to do a hard one. I just want to do a fairly easy one. I just want to do this
Oh, I
one.
thought you were doing the S squared.
No!
And I was like, that doesn't.
True. This is non-homogeneous. I'd have to do that whole where A is equal, you know, and oh, I don't want to do that. Not today, friends. Not today.
You're safe. Your cheat room is here.
No, but you're in a happy place. No. 6. And x prime of 0 is negative 2, let's say. Whatever. So, I'm going to transform this thing into s squared times x of s minus 6 times s plus 2. This thing right here is x double prime. Look at it. Stare at it for a moment. Make it feel uncomfortable. Plus 5 times, right? Right? S times x of s minus 6. It's not random, yo. There you go. Plus 6 x of s, we just convert that straight across, is equal to, wait for it, 3 over s squared. How did I get that? Because what is the Laplace transform of t? It's 1 over s squared, yes?
Yeah.
So the Laplace transform of 3t, 3 over s squared.
Aren't you missing something then?
Bro, that's it, man. This is x, look right here. This is x double prime. Here is 5x prime.
Should you have a minus?
I got it, yo. And here's my plus 6x right here. There we go. Now,
Oh,
Let's-
the 6 is the
ah!
X. Isn't it?
So let's distribute this mess out a little bit. Oh, they're so cute. Now, if you pay attention over here, we have 1, 2, 3 x of s's, yes? Let's put them together, shall we? So if I collected my like terms, I would have this many look at it.
Characteristic equation.
There's our characteristic equation again. But we're not done with him. Is he plus or minus 6s, I should say, minus 28 is equal to this fella right there. So of course I want to solve for x of s. That's the whole point. That's why I said it's a giant algebra problem now. So what are you going to do? Well, we're going to minus, so plus 6s plus 28, yes? And then divide the whole thing by s squared plus 5s plus 6. And this is equal to x of s. Now quick, where did this come from? I don't know yet, Donovan. Hold your horses. Now, Donovan, because I'm a mean person, no, actually that's not true. I really want you to understand where this comes from. I'd like to get a common denominator up top, yes? Which of course would be s squared, right? So this is going to become 6s cubed plus 28s squared, yes? All right, that's cute. So what I'm going to end up with on top is 6s cubed plus 28s squared plus 3, right? Over s squared over the denominator. So in other words, in the denominator you're going to have s squared and then s squared plus 5s plus 6, right? This is a fun deal. Now, potato, vodka. If I were to write that in factored format down here, I don't know. And you saw that, and you were back in Calc 2, what would you do if you saw a problem like this? Partial fractions! I know. So let's do it. So, it's going to be what? It is going, no!
Oh, never did.
It's going to be a over s plus b over s squared. Remember, you have to do it twice if they're repeated roots. You've forgotten. Don't worry, you'll remember. Plus c over s plus 2 plus d over s plus 3. So we are going to expand this out using partial fractions. But the good news is, Donovan, I'm not going to make you do them this way. But Donovan, if I did.
No way.
But Donovan, if I did. If this was a 7 on top. Donovan, this would be 7 e to the 3t, or e to the negative 3t. If this was a 2 right here, this would be 2 e to the negative 2t here. Donovan, by God, if that was a 2 right there, it would be 2 over t. It would be 2t, I mean. Right? And Donovan, by George, if that was 1, we didn't do 1 over s, but 1 over s is a constant. It's 1. So, what I want you to do is take your calculator, and we're going to use the expand function. 1 second, man. I'm on a roll. So under F2, now on the easy ones, of course, knock yourself out. This is ridiculous. I'm not going to do this nasty one by hand. I'm just never going to do it. I'm going to do this. I don't care what variable you use, although I'm probably going to use z. Okay. So I'm just going to go 6z cubed plus 28z squared plus 3 divide by, and I'm going to just go z squared times parentheses. And you don't have to do it all the way out like that. I mean, the way I did it, I could just do z squared plus 5z plus 6. Oh, hippie. Bam. There it is. Okay? Somebody didn't screw it up. Okay. Can I borrow a calculator? Of course you can borrow a calculator. All right, what you got?
I seem to recall that when we were doing the partial fractions last year, if the term on the top of the fraction wasn't a constant, I recall that we added like an extra.
No, if it's on the bottom. If it was on the bottom, if you had s squared plus 4, you'd have to put like two. You'd have to put AS plus B on top.
Yeah.
That's not what I have. I don't have any of those. But only if you had like a non-factorable quadratic, like s squared plus 4. All right. So what do we got here? So we got 31. Negative 31 over 3 is my constant. Yes. Donovan, is that what you got? You want me to write it out, Donovan? By George, I'll just write it out for you, Donovan. I don't know, Donovan. It's fine. Right? And then what's the next one? Levi, what's the next one?
Oh, it's 67 over 4.
Then 1 over what?
1 over s plus z plus 2, s plus 2.
Whatever. And then
And then negative 5 over 12 z.
1 over, oh, 1 over z. I'm going to write like this. So
Yeah.
1 over.
And 1 half, 1 plus 1 over 2, 1 over s squared.
Okay? So, this thing here, when I see 1 over s plus 3, I know this is e to the negative 3t. So the constant just tags along. So it's negative 31 thirds e to the negative 3t.
In this case, would
Plus 67 fourths e to the negative 2t.
so it wouldn't stay in terms of s. It would,
No, that's just the, now we're taking, check it out.
now we're going back.
Now we're doing the inverse
The jump in the way back.
Laplace transform. We never used s. You're right. We didn't. It was just like a filler. That's all it really did for us. And then this guy is going to be negative 5/12 because this guy here is just 1. And then it's going to be plus a half t. There's my answer. That's it. Bam. Bam.
The last one, that's 1
1 over 2t. 1 over 2 times t. Half t. T over 2. Now, here is another one. Now, you already know the answer going into this one. You already know. Oh, for gosh sakes. Just a minute. I'll go back to it. Yo, I'll go back just a second. Don't get mad. Don't get mad, bro. No. Hey, what now? What did you want? Go back? No, go back. Like that?
Yes, like that.
Sure. This is x of t. That's what I wanted to find out. Right? That was the whole point. And fairly painless. And by the way, once you get good at it, pretty fast. Right?
I mean, if we were doing it all with the calculator, right, then it'd be like 2 or 3.
Well, literally, okay, so you just type into a solver, yeah, boom, done. But that's not the point. Yes, but yeah, on a calculator, you transform it. You can literally type in solve the original equation, and it'll solve for x of s. And then you could just then you could then have it expand it, and but then you have to actually figure out which ones are which, where they come from.
Laplace.
On inverse Laplace. Yeah.
Is there like a Laplace
No.
button?
No.
That'd be
But
I'm sure you can find like a web.
dude, there's calculators out there. Yes, online, for instance. Simbo Lab can do it, for instance, right there, where you just type it in. But listen, that's not the point. The point is to understand where it comes from.
Can Wolfram do it?
Yes, Wolfram can do it too. What?
What is the inverse Laplace transform actually defined as?
You're just going back from one back to the other. If you want to know the actual how it works and where it comes from and stuff, that's a linear algebra question. But we're not worried about it in this class per se. Why not 5? I'm not doing any more freaking 5s. I'm getting rid of this 5 too. Make that a 12 or something. I'm sick and tired of freaking. Now, all right. Clearly, this one over here is going to be a cosine and sine business. Yes. I know this because it's going to be r squared plus 4, and yay. So I'm not shocked by this. So in a minute, I'm going to get cosines of 2t and sines of 2t probably, yes? So I'm not going to be shocked by this. By the way, my other side is going to be cosine of 12t, isn't it? So when I'm done, there's going to be a part of this that's going to be cosines of 2t's and sines of 2t's. And there's going to be some of it's going to be sine of, or cosine of 12t's as well. So I'm not going to be shocked by this in a few minutes. By the way, that means I'm going to end up with something like this. Right? Because that's cosine of 2t, isn't it? Yeah. And I'm going to end up with something like this. I don't know what's going to be on top. I'll put some a on top. I don't know what it is yet. I'm going to end up with some sort of a sine of 2t. Further, I'm going to end up with something like this. Oops. Ah! 144. Right. K squared. In a minute, those guys are going to pop out. Right? They will pop out. But they're not there right now. Now, let's try this. So this is going to be x or s squared x of s minus 4s minus 7 plus 4x of s equals 3s over s squared plus 144. Yeah, we're not. But yeah, I mean, this is literally right here. What you could do if you want to do this on your calculator, but I don't want you to. But you could. We will do it later on. When we do systems, we'll do it this way. Later on, we will just not act. Once you've done, once you see an s show up, you'll just assume these are functions of s. So a lot of times I'll just drop that later on, especially when we get to systems of equations. You got s's and x's and y's and all that. Just leave this to be s squared x, and then 4x here, and then we can actually use this to solve. Have the calculator solve for x, and then expand whatever for an answer. But let's keep going here for a sec, see what's up. So break out your x of s. That leaves me with s squared plus 4, big surprise. Look at it.
Oh, you moved it over.
There you go.
Good.
I'm sneaky like that, dog. Okay. Now if you expand that on the calculator, this is one, Brandon, where you have to do it. If you did it, you'd have s squared plus 4 and s squared plus 144. You'd have to have as plus
Okay.
b on top.
That's only when the bottom can't be factored
Correct.
without using imaginaries.
Right. So,
Wait, is it s squared plus 4 on the bottom?
yep. Right? Why? Why? Because it's from the s squared plus 4 on the other side. Right?
Oh, okay, that's like the one. Oh, 4 times. Oh, because that one went there. That's why I was looking at the wrong thing.
Oh, yippee. That's it right there. Is that what you got?
Yeah.
So it's -3. So -3 over 140, is that right? And that's s over s squared plus, what was it?
140 plus 144.
What's the next part?
Plus 563 over 140 times z over z squared plus 4.
Ah,
Or s, sorry. And then plus 7 over s squared plus 4.
right?
Are you shocked?
No, I am not shocked. Now look at this right here. Check it out. That guy right there is cosine of 12t, yes? So there's -3 1/40ths of him. Okay? Now, this right here is cosine of 2t, yes? So there's 563 1/40ths of cosine of 2t. Now this next one's a little tricky. What needs to be on top for this to be signed? No, I don't know.
You can have 2.
There needs to be a 2 on top, yes?
Yes.
So stick a 2 up there and divide by 2. So plus 7/2 sine 2t. That right there is the answer that you went to seek. that?
A lot nicer than normal.
It is kind of nice, isn't it? It is kind of nice. So, yeah. So, if it was homogeneous, I mean, literally, if it's homogeneous, I don't know why you're using Laplace, okay? It really, Laplace only really shines when it's non-homogeneous. You got some gross mess on the other side. But for instance, let's just try this one. This is the last one. We'll call it a day after this. I'm tired. Oh my gosh, that's gross. It's not gross. Quit being weird. Quit being a drama queen, you. Why is there a 5 there? Idiot. Whatever. So it's s squared x of s minus 4 times s minus 2 plus 3 s times x of s minus 4 plus 2 x of s. Now, what is the Laplace transform of t e to the AT? We did it earlier. I believe it's 1 over s plus 3 squared. And then this is going to be plus 10 over s. Right?
Yeah.
Huh?
1 over s. Oh yeah, negative 3. Actually,
Bam! So, if you fold this out, this is, I'm just going to write it here, 3s x of s minus 12. So, because you know it's going to turn out the same way every time, do this part right here without writing anything else down. Just do this. Why is that a minus? That should be a plus, you idiot. And then plus 2. And then everything else is going to get put over to the other side, yes? So this crap's already over there. And so I've got a 4s. I'm going to add that over here, plus 4s. And then I've got a minus 14, so I add that over, I get positive 14. And then, divide by parentheses s squared plus 3s plus 2. That is as hard as it gets. Once you get here, it's the same thing every single stinking time. It literally, it really feels like after a while, it's like I got this thing by the tail, and you do, because it's not very hard. Done.
you shouldn't be happy.
All right, so is that what you got? So 3/4, and then it's 1 over s plus 3, right? Is that what I got? No. Right. And then what else?
1/2 1 over z plus 3 squared.
Okay.
And negative 2 over z plus 2.
What? Negative 2?
Negative 2 over z plus 2. Or 1 over z plus 2.
And then,
And then 1/4 1 over z plus 1.
cool.
And
One more?
5 times 1 over z.
Ah. Okay, so start here. This is 3/4 e to the negative 3t. All right. What's this right here? This is a half t e to the minus 3t. All right. Plus, this is negative 2 e to the negative 2t plus 1/4 e to the negative t plus 5. Thank you. And we're done. That's it. Now, can you see where all those pieces came from?
Yes.
I think so, right? Because then you got on the bottom there, you get s plus 1 and s plus 2. That's these fellers, right? Where did these guys come from? Well, listen, if you have this guy right here, right? He is part of a double root, yes? A part of a double root of e to the negative 3t, right? So, wherever there's e to the negative 3t twice, you're going to have it once. That's here. Plus its double root version. And then, oh look, there's a constant. Well, I'm shocked. There was a constant above. I'm sure there's going to be a constant down here. All the pieces fit where they belong-ish. So you should be good to go. Okay? You can see if that's Smith. If it is, just say Joe's Bar and Grill, and I'll be right there. All right. For those of you who be gone,